Hi, my name is Brandon LaFleur, and this fall I will be a senior at the University of Michigan studying nuclear engineering. This summer I worked under Dr. Sarah Pozzi and Jennifer Dolan. My research involved characterizing two different types of liquid scintillators, as well as looking at various simulation techniques in the program MCNPX Polemi. This work is important in the application of nuclear non-proliferation, specifically in the characterization of special nuclear materials using neutron coincidence collars. So we're here in the lab where we took the measurements, and this is the first detector we'll be looking at. It is a 3x3 cylinder organic liquid scintillator. It's the primary geometry used in our research group right now, one of the reasons being that this PMT covers the entire backside of the detector, which is great for light collection. One of the motivations for this measurement was to see if these larger square geometries could be used to replace the cylinder geometries for these new neutron coincidence collars. One of the concerns is that these PMT does not cover the whole backside of the detector. It's a much smaller percentage of the total surface area, which is not good for accurate pulse shape discrimination. Another concern is that there are longer possible neutron flight paths, which may distort timing information. So, in the following slides, we will be looking at pulse height distributions, PSD performance, and cross-correlation plots for both the detectors to see if they compare and to see if there's significant data loss if we were to switch to the square detectors. We will also be looking at simulating both the geometries, because you want to be able to simulate them with some degree of accuracy, but I'll explain more about that when we get there. Using these identical orientations for the two detectors, we measured a fission source which emits both photons and neutrons. In this case, californium-252 was used. Using a common PSD method, these plots show how well the detectors can sort out photons and neutrons. The main concern is for lower energy pulses where photons and neutrons are harder to separate. This slide shows two zoomed-in PSD density plots. You can see that the square detector has a slightly worse resolution for lower energy pulses. However, it does perform quite well and would be able to be substituted for the cylinder detectors without significant loss in information. Ignoring the absolute count rate difference, normalizing the count rate shows very similar shapes. This is encouraging because it shows that the square detector can perform at a very close level to the cylinder detector. Shown here are the normalized cross-correlation plots of both detectors. Again, very similar results, differing mainly in a broader distribution for the square detector. This can be explained from the relatively longer travel times available for neutrons striking the detector face. These measurements allowed us to come to the conclusion that there is no major difference in the performance between these two detector types, and that the square detectors could be used in place of cylinder detectors in the application of a neutron coincidence collar without significant performance loss. We will now change gears and look at how the program MCNPX Polemi and MP-Post simulate both detector orientations. MCNPX Polemi simulates the radiation emitted from the source and the particle transport through the material. MP-Post takes the simulation data and processes it to simulate detector response. This includes type of interaction, as well as timing and energy information. There are currently 4 options available for users to simulate californium-252. These simply correspond to how you input the source into the code. A negative source simulates isotropic emission, while a positive source means anisotropic emission, which more closely reflects reality. Source 1 takes into account differing energy spectra resulting from differing multiplicity, while source 10 does not. As you can see, the cylinder PhD simulations compare very well with the measured data and do not differ from one another drastically. These plots show both the positive and negative source 1 pulse height distributions. These plots show the cross-correlation agreement for the positive and negative source 1 and also agree quite well. The same can be done for source 10 and negative 10. I have put in this table the average relative errors for each of the 4 sources, with the top performing source highlighted. It is clear that this negative 1 source gives us the most accurate results. The square detectors were harder to simulate with any accuracy, however. This is because we have not done much research into how the light collection differs with the square geometry. The following results will shed light on how accurately the 4 sources simulate californium-252, but are less conclusive than the previous results. More research will be needed to simulate these detectors with any confidence. As you can see, the PhD simulations behave similarly, but do not match with the measurements as closely as the cylinders did. Here, the very different shapes in the cross-correlation plots show us what we already know, that the light collection is not yet properly simulated for these detectors. The same is done for the -10 and +10 sources, and this chart shows their average relative errors. Again, the -1 source performs the best. This fact, along with the previous results, suggests a few things. First, more research is needed to improve the light collection coefficients for the square detectors. More precise and longer measurements with more specialized equipment are needed to obtain these. Second, the simulations could be run for longer periods to reduce statistical error and give more authoritative results. Third, the simulated geometries are very simple. By adding features such as the floor, table, PMT, and walls, more realistic simulations could be performed to obtain more realistic results. And lastly, the fact that the -1 source performs the best suggests that there may be something wrong with the way the program simulates anisotropic emission. However, more conclusive results would need to be obtained to prove this the case. I would like to thank Dr. Pozzi and Jennifer Dolan, as well as the SURE program and the whole DNNG group at the University of Michigan for working with me this summer. Thank you.